In this talk, I want to cover the big picture of the past, the present, and the future of the smart contract landscape. And then I want to dive deep into what we in the smart contracts team within Parity have been working on, and the engineering challenges we faced, and how that fits into our vision of a smart contract future. I only caught the end of the previous talk from Super Colony. As somebody who works on the Inc. team full-time, it's really gratifying to see external teams taking our technology and building cool stuff with it. It's fantastic to see. So by the end of this talk, you will, I hope, understand what is the story with smart contracts in the .sama ecosystem, and what makes it totally unique, and how you can use our technology in the present, and what the future will look like. So let's start with the past. Now, the blockchain world moves fast. So blockchain years, they're like dog years, so the very recent past can seem like a long time ago. So in ancient times, the smart contract world was a simple one. We had specialized sovereign smart contracts, so-called L1 chains. What do I mean by specialized? Well, the only thing they can do is run smart contracts. Composability is the superpower of smart contract blockchains. So trustless on-chain interaction between independent contracts. You can build applications that are bigger than the sum of their parts. Languages, limited language options, the most popular being Solidity, a specialized smart contract programming language. Has its benefits, very popular, but it's another language to learn, and it might be my own echo chamber, but I don't hear a lot of love about Solidity. Scalability is limited by the block size of that individual blockchain, so there's a fixed finite limit to the number of transactions you can process. So what's the story with smart contracts on Polkadot? It's a more difficult story to tell because Polkadot is agnostic as a so-called layer 0 protocol. You can't deploy a smart contract to Polkadot directly in the same way that you just deploy to an existing layer 1 smart contract blockchain. Smart contracts, of course, are deployed to parachains. So it's open to a parachain to any number of smart contract implementations and execution environments. And if an individual parachain wants to enable smart contract functionality, they have to either build it themselves or use one of two out-of-the-box smart contract palette implementations, which have come out of, which originate in Parity. So the first one is palette EVM, and that enables, of course, direct porting of Ethereum-based apps into the .sama ecosystem. Obviously, some very well-known parachains are using this palette to enable smart contract functionality in their parachains. Now, I'm an outrageously biased member of the Wasm Smart Contracts team in Parity, so I'm not going to talk about EVM today. It's great, many teams are building with it, and it's here to stay. I hope I'm not the only one old enough to understand the cultural reference, but I'll just leave that there. What I'm interested in is the contracts palette and the Inc. programming language. So the contracts palette is a module that can be plugged into your parachain to enable WebAssembly contracts. So we love Inc., which is a language built on top of Rust to allow programming WebAssembly smart contracts. And that little logo between Drake and the WebAssembly is called Squink, and they are the mascot for the Inc. programming language. Look out for Inc. swag. So I guess all of you were here for the previous presentation where he went very in detail into Inc. But in case you've been hiding under a rock, that's what a very basic Inc. Smart contract looks like. And if it looks like a Rust and quacks like a Rust, then it probably is just Rust. It allows you to write smart contracts in Rust, and Inc. provides the magic to generate all of the boilerplate code so you can focus on the business logic. This is a screenshot from the recent Stack Overflow developer survey. Rust, top of the pile again, I think for 5, 6, 7 years in a row, I don't know, but what it shows is there are a very big pool of potential developers who love Rust and want to program smart contracts in Rust. I count myself as one of those. So we'll give a quick overview of our stack for those who are not familiar. So Inc is our programming language, as I've covered, that is like a Rust DSL to produce code that will allow writing smart contracts in Rust. And then we provide a tool called Cargo Contract, which compiles and optimizes your contract and allows us to optimize the code size and do extra steps such as linting to make sure your smart contract is valid. That produces the artifact of a contract file, which is bundled with the metadata that describes the ABI of the contract, and that's for UIs and third-party tools. And then eventually you deploy that to a parachain, which supports the contracts palette, and where you can execute your smart contract. So who are we and who am I? On the left there is the Inc language team I'm part of, and in the middle is the team working on the smart contracts module itself. And under the umbrella, we also have a user interface team that builds the contracts UI, which is an alternative to the Polkadot.js UI for interacting with smart contract-enabled parachains. And a special mention to a couple of people whose faces don't appear in the hexes there is Robin, the original brains behind Inc, and Sergey was the guy who created the contracts palette in the first place. And also our biggest external contributor at the moment is XScreenX from SuperColony. He does a lot of good work for us, so I want to shout out to him. So what motivates us? So we want to be the default and the most popular choice for parachains who want to enable smart contract functionality. In order to achieve that, we need to be the best, or at least competitive, in terms of safety, which is super important for smart contracts, which manage a lot of economic value. Performance, it must be able to fit a lot of smart contract transactions into a limited block space. And scalables, we need to provide cross-chain primitives for composability. And a pleasure to work with. So that's where the Rust language comes in again. And finally, we want to provide a low barrier for entry for developers who want to deploy something on-chain today. So as you can with most other smart contract chains, without building your own Substrate node, without bidding for a parachain slot or a parathread. And then if you want to migrate your application to a full blockchain, it's easy to port the Rust code into a Substrate runtime if necessary. So back to the present. So the overall smart contract landscape has many sovereign, independent smart contract blockchains. Interoperability is through insecure bridges. Scaling is via layer 2 chains, and there are different standards and different levels of trust. And of course, there's the nascent .Sama ecosystem with its parachains and XCM, and we'll come to that. So that's what the landscape looks like at the present. So as far as we know, we're building something totally unique, a fully sharded, heterogeneous blockchain network. So true scalability by scaling out, and secure and trustless interoperability. However, there are limitations and engineering challenges, and now I'm going to dive down into some of the things we've been working on internally to address those. So the first limitation is a familiar one. It's block size, also known as block weight. Because of the mechanics of the parachain consensus, we have quite a long block time of 12 seconds, which is double the relay chain block time. It's because the parachain blocks requires the hash of the most recent relay chain block, and it moves in lockstep with the relay chain. And also the amount of execution time out of that 12 seconds is very limited. Only half a second out of 12 seconds. And in reality, it's limited even more because 75% of that is only allowed for normal transactions. The rest is for operational transactions. So we as a team spend a lot of time measuring and optimizing the performance of our WebAssembly contracts and the execution environment in order to fit as many transactions as we can into that small amount of time. At the end of last year, when we were first considering launching the contracts palette on parachains, we realized there was another limitation which is not a consideration for traditional smart contract chains, and that is the POV size. So POV stands for proof of validity. So relay chains need all storage items as part of a transaction to verify the state transition of a parachain block. In our case, the storage items are the contract code itself, which in turn has to be executed to verify the state transition on the relay chain. And the size of the POV message in the middle is limited. So when you're executing multiple contracts in a single block and the total size of all of the blobs of contract code exceeds the maximum size of the POV message, then that will limit your throughput of smart contracts. So we've spent a lot of time since the end of last year trying to address this issue. So one of the first things we've done is we've looked at reducing the size of the contract code which is produced. As much as we love Rust, it does produce a lot of code. It's not the most efficient in that respect. So we've done some work optimizing that. As an example, we managed to reduce our ERC20 example contract down from 30 kilobytes to 8 kilobytes. Now, how have we done that? So by far the biggest reduction was from simplifying some of the built-in Inc data structures. So we replaced ergonomic but code-heavy data structures which were optimized for caching storage access. Storage access is expensive, and replace that with some simple mapping primitives. That's one thing that we've done. And we've done some kind of nitty-gritty, time-consuming optimization of the Inc code generation. There's a lot of small gains, but the small gains add up to some big gains, and that is a continual area of improvement we're looking at. And finally, because we have control over our build tool, Cargo Contract, we're able to experiment and tweak some build parameters, and also we have control over the post-compilation Wasm optimization step, so that is another area of research into reducing the code size. It's something we're measuring constantly, looking out for further incremental improvements. It's important work, it's not very sexy, but that's one thing that we're spending quite a lot of time on. So what does the future look like? First, I'll highlight some of the solutions that are coming down the track to address some of the challenges I highlighted. And then I'll talk about what we think the future will look like. First, a solution that is in the works by Rob Habermeyer to address the issue of limited parachain block weight, aka execution time. Last time I checked, it was called async backing. It might be called something different now, but it allows parachains to build blocks in parallel with the relay chain, because it doesn't need to wait for the hash of the most recent relay chain block, but rather it can use one of the ones that came before that, so it allows it to build it in parallel. So remember this diagram? So in theory, async backing, if it works as intended, can not only reduce or increase the execution time, but it can reduce the total block time. So we could see potentially, obviously these numbers are only potential and have not been proven, but in theory we can see as much as a quadrupling of the execution time, and if you halve the block time, you get twice as many blocks. So yeah, that's been worked on by another team within Parity, and I hope we can see that soon. Within our team, we're looking at another way to maximize the throughput, which is to speed up the execution. And currently we have two active areas of research. And the first one is to look at speeding up the Wasm interpreter. There have been some experiments which can show a possible 50% improvement, performance improvement of the Wasm interpreter, which will actually execute your Wasm smart contracts. So that's a promising avenue of research. The second area is we've looked at just-in-time compilation. So instead of interpreting the contracts, we compile them first before executing. It remains to be seen whether this will be overall faster once you include the time once you include the compilation time together with execution time, and whether it's worth the extra implementation complexity, and there are other risks associated with compiler bombs. And for solving the problem of large contracts having to be sent across the network as part of the POV, one long-term area of investigation is the possibility of using something called code merkleization. So instead of sending the entire contract code blob, which could be quite big, it involves sending only those parts of the contract code that are actually being executed as part of the POV message. Now the exciting stuff. So composability is the real superpower of integrated smart contract networks. And since the future of smart contracts involves cross-chain, cross-contract calls, what does that look like? So XCM, you've probably heard that already. Last time I checked, it stood for Cross-Consensus Message Format. And there are many other acronyms to go with that. But let me show you some of the primitives that we're looking at, including in the contracts palette and in the Inc language, to allow usage of XCM directly from Inc smart contracts. So here you can see the send side of the equation. Very simple method, and in the argument location can be a multi-location addressing a different smart contract on another chain. And the receive side, again, very simple, very low-level API. Smart contract can receive and process the message. It's a very low-level and raw API to start with, but we can build some abstractions on top of that for a good story for async cross-chain, cross-contract communication. Okay, so what do I think the future looks like in smart contracts? Extremely optimistically, I want to see smart contracts on every parachain, just like every parachain has the balances palette. Okay, not every parachain, but yeah, like I said, I'm biased. Smart contracts on a specialized chain would allow calls into the runtime of that chain via chain extensions. So you can see the potential for permissionless smart contracts on even chains which are not smart contract specialized chains. And true scaling, of course, is achieved through parallel execution, right? So yeah, bigger numbers rather than just focusing on optimizing the throughput for an individual chain. My moonshot is a Wasm Contracts common good parachain. Now, excellent teams are already launching pallet contract support in their parachains. Originally, we did plan to launch our own common good Wasm Smart Contracts parachain. That plan was shelved. We believe in a decentralized ecosystem, and minimize what is built and operated by Parity, and it allows us to focus on the core tech. That being said, my hope is that in the future we'll see such a common good smart contracts parachain launched, where I can, use my DOT or KSM for contract execution, otherwise known as gas. What the incentivization model will look like is an open question. It could possibly be funded by the Treasury. So I'm just putting that out there as a moonshot. It's not something we're working on, but as a user of .ksm, I want to be able to pay pay for my smart contract execution with those native tokens. Right, call to action, check out our code on GitHub, do one of our Ink tutorials, come and chat to us on Element and Discord.